Hi everyone, can you hear me? So welcome to the second session for today. I'm Kenzie, and yeah, if you can, everyone just take a seat, we'll get started right now. Okay, so the first talk for today is Yin-Zhe Ma, who's going to talk about cosmological uses of fast radio bursts. And this is a 20-minute talk with 5 minutes for questions.
Okay, thanks for the organizer to give me this opportunity, wonderful opportunity to present my research to this long expected symposium. And when Ben and Vanessa organized this in 2020, I wasn't completely sure that this will happen, actually. So certainly Ben and Vanessa put a lot of time and effort to organize this event, so I sincerely appreciate their work. Okay. So my name is Yin-Zhe Ma, over here, and I'm currently a professor at the University of KwaZulu-Natal, South Africa. So I'm a cosmologist, so my research is about using FRB to understand the universe as a whole. So when you look at the FRB, the pulse travels through the lossy structure of the universe and is influenced by the intervening gas, which sit in the gravitational potential. So therefore, the DM measurement encodes a lot of information on the cosmic web. So in the past years, I've done some work with my ex-student Charlie Walker and postdoc Anthony Waters on using these FRBs to understand the cosmos in general. So I attribute a lot of results shown here to these two young researchers. So this talk is full of imagination. Yes, of course, this is a feature of cosmology. For example, you don't see the age of the universe. You don't see inflation, quantum fluctuation, Bunch-Davies vacuum, and you certainly cannot see neutrinos. But these are essential targets in cosmology, and people strive to build expensive experiments to measure. So today I want to give some, does this flip? No? Okay. So today I want to give some holistic view of the connection to cosmology and provide some new thoughts and angles on what one can do with some reasonable size of FRB catalogs. And if my talks make you interested in these problems, I have done my job. So my talk consists of two parts, the cosmological constraints with FRBs and IGM, CGM constraints with FRBs. So what does this, okay. So what does the DM cosmos made for? We can deconstruct the DM by separating them into diffuse components, stellar components, and interstellar components. So F star is a fraction of gas which is already made into stars and galaxies, this term. And F sub IGM over here is the interstellar medium components. Therefore, the DM IGM is directly proportional to the baryon fraction. So it's sensitive to the diffuse gas in the universe. And for the future cosmological constraints, we did a forecast for a large number, a reasonable number of FRBs. One of the experiments one can realize in the southern sky in South Africa is a HIRAX experiment. So HIRAX stands for the Hydrogen Intensity and Real-Time Analysis Experiment, and it's an international collaboration which my university is driving, and it contains about 1,000 6-meter dishes operating at 400 to 800 megahertz. And science targets contain both the baryon acoustic oscillation signals and also the FRBs. And due to the southern hemisphere, it's complementary to the chime observations, and location have very low RFI and no snow throughout the year. So, all right. So we not only locate in the Karoo Desert where SKA sits, but also extend further out to the other African countries to enable the long baseline interferometry. Okay, so this is a forecast for a significant boost of the angular resolution with HIRAX, and it can achieve arcsecond resolution over here, and with the outrigger array elements that extended further out. So we can really pinpoint the spiral arm location and such. Okay, so however, if we assume a number of localized FRBs, roughly 100 or 1,000, which is a reasonable number achievable for HIRAX or chime-like experiment within a year, to redshift about 3, and launch a chain of Markov chain Monte Carlo with other like other cosmological data like CMB and BAO from galaxies, supernova, and H0 measurement, we found that the final measurement does not really improve too much. So if you look at these curves, they are really close to the non-FRB results. So apart from this omega baryon H² measurement, so all of the other likelihoods are fairly close to each other. So in that sense, FRB does not improve too much on the existence of the figure of merit of the known data. And here in the left panel, we plot the constraints on the omega matter, the fractional matter densities, and omega baryon H² plane. And here we include the CBSH, the CMB data plus BAO plus supernovae plus H0 with FRB1 analysis, and plot the resulted constraint in the gray one for FRB only, but the other one is combined with other standard cosmology data. And you see the degeneracy direction of the two eclipses are different, and their intersection give a combined constraint in blue. And the same for the right panel here. The degeneracy direction of the two bananas are almost orthogonal between the FRB one and the other cosmological one, and the constraints can be tighter up on that direction, on the cosmological one direction. And it's greatly constrained the omega baryon H². But the other parameters, like it's really hard to tell too much about the matter densities and cannot tell too much about the curvature of the universe. So we conclude that the omega baryon is actually what he's searching for. And now we evolve to the second question of using FRB to probe the intergalactic medium. And everyone knows this pie chart, which shows that only 4.8% of the cosmic budget is known for its origin, the atoms. But where are these atoms? Right? So FRB is certainly one technique. The large dispersion measure from the integrated value of electron density along the line of sight can tell you a lot of this. So relevantly speaking, the DM Milky Way is well known from galactic pulsars, and DM holes is not well known, but for high redshift FRBs that it is subdominant. And so for high redshift FRBs, the DM IgM is dominant over here, and it's mainly the cosmological information. So 2 years ago, the J.P. McQuaid published his milestone papers of calculating the baryon density with the 6 localized FRBs. Okay, with this number. And another measurement, of course, coming from the microwave background radiation, the reason is that at early universe, the baryon and photons mix as hot plasma, so the baryon density affects the speed of the acoustic wave. Therefore, by measuring the angular power spectrum of the CMB, one can determine very precisely the baryon fraction. So the upper panel is the full sky temperature anisotropy measured by Planck satellite, which I was heavily involved. And the lower right panel here is the exquisite power spectrum measurement from Planck. And this is the value we obtained. This value is what we obtained. Okay, and the third measurement is a measurement of the deuterium abundance of the preceding gas in the damped Lime alpha Fourier measurement system. This is a quasar emission system, this one, so any distant quasar will give you a continuum spectrum, and you can use a prominent Lime alpha peak to determine its emission redshift. So while the quasar's radiation penetrating the IgM towards you, the whole spectrum is shifted to the longer wavelengths, which is the redshift effect. And there are many absorption trough along the way, so you can use the absorption trough, the metal poor DLA system, to measure the primordial deuterium abundance. And this is the result of the measurement. The middle panel is the deuterium abundance normalized by hydrogen abundance. You can see that the deuterium is remarkably sensitive to the baryon densities. And this is because deuterium is a middle stage to form helium at the first 3 minutes during the Big Bang. So it's very, very sensitive. And the most state-of-the-art result coming from this Cook et al. Of measuring a number of these metal poor DLA systems, and they can measure omega baryon H² here. So if we put together these 3 measurements of the baryon densities from 3 completely different observations, the damped Lime alpha Fourier measurement over here, the CMB measurement from the Planck, and the FRB measurement from McQuaid et al., the 6 localized FRBs, we got remarkably consistent numbers. Right? Isn't this impressive? Right? This just means that if you know what happened at the first 3 minutes of the universe, you almost know what happened at 400,000 years after, and also indicating what is going on billions of times a year later in the IGM. So if this doesn't impress you, you have no soul. That's what I feel. That this is really something, it means that it really works. Okay. So my mind, in cosmology mind, the baryons are never missing. They are there, but we haven't counted enough of them at low redshift. So can we pursue them? Right. So numerical simulations early on have shown that the abundance of these diffuse baryons. This is the early hydro simulation by Sen and Oestreicher. You can see that the majority of baryons at low redshift over here, is mainly in the phase of the warm-hot intergalactic medium, with temperature in between 10 to the 5 to 10 to the 7 Kelvin, the red curve showing on the graph, the red curve over here. So, but X-ray observations is mainly observing the center of the clusters because the flux is proportional to the electron density square. So it's really sensitive to the high density peak of the clusters. But FRB can sample this pretty well because its line of sight measurement is almost a direct measurement of the column density. So it gives fair weight on the diffuse emission part. So just as cosmological constraints, now we turn it around and use a hypothetical 100 and 1,000 FRBs from Hyrax-like experiment to constrain the IGM. And we can generate the FRB source redshift as a log normal distribution at different redshifts over here. And we can model the gas evolution in 2 ways. One is the constant gas evolution. The other one is the redshift evolution with this form, which is indicating from the numerical simulations. Right? And this is a result of the constraints of the diffuse gas from this mock catalog. And we combine the mock FRB catalog with the CMB measurement from Planck and the baryon acoustic oscillations from the EBOS and Type 1a supernova. And we can constrain the F-gas and the other cosmological parameters which are sensitive too. And one can see that with just 100 localized FRBs, 101, which is the blue one, we can find a typical constraint on the F diffuse of a few percent. And with 1,000, which is showing here as the orange one, the constraint can be quite remarkable, which is roughly about 5% or below. This will tell us a total evolution of the diffuse gas across different redshifts. But this is a total evolution. The overarching question is still be the location of these missing baryons. And the left numerical simulation here shows that the quantified baryon fraction in clusters, filaments, and void. It turns out the fraction of the mass is highest in the filaments. Why? Because although the halo density is much higher, they are rare, so the filling factor is small. Whereas the void, which are underdense region in the universe, is really ubiquitous, but the density is low. So the filament is a location where it holds the balance between density and filling factor. So it does have the highest contribution to the baryonic mass. In the right panel, it was our previous work of detecting the gas in filament through the Senyayev-Zerdovich effect. I'm not going to any details, but we found 5.3 sigma detection of the effect of filament gas around 10 to the 6 Kelvin, derived from these equations. So this will be mainly where the gas comes from. Right, so also the numerical simulation from Illustrious shows that the baryon is also somewhere in the filament and in the void. And so in this graph, if baryon completely trace the underlying dark matter, then all of the points should fall in on this line, on this slope with the cosmic mean fraction. But however, you see that for halos, it does have a high dark matter density and high gas density, but relatively speaking, there is some gas removed from here and being blown away into the filament and voids. So you see a deficit of the gas fraction in the halo, but a slight increment in filament and more increment in halos. But why is that? Oh, the answer is feedback. This is a movie, but now I can't show the movie. We can only upload PDF. But the stars is actually an isolated object put together by gravity, and gas is extended much further out from the center of the clusters into filament and void, shown here. And gas temperature can also be very high in the center of the clusters, and but feedback will drive the gas into the filament voids, mainly AGNs, and realizing the modulation I showed in the last slides. You can see the metallicity also grow as a result of nuclear fusion in the center of the clusters.
You have 5 minutes left.
5 minutes, okay, no problem. Right. Okay, this is a statistic from the previous simulation. These are appreciable fractions in the filaments shown here, and shown in the red circle, almost half the baryon mass is actually in the filament, and you can also directly see them in the snapshot. And the results of baryon are separate, half resultant half in cluster, half in voids, but the majority of them are in the filaments. Okay, and let's see the next one. Okay, right. So the upper panel is redshift evolution of the baryonic mass. In different morphologies, you can see the gas in filament red curve is highest portion at low redshift, whereas the halo and voids are appreciable over here for gas. But for dark matter, void is really empty, and halo and filament share roughly half of the densities. Okay, so void is really empty for dark matter, but not for gas. Okay, what about FRBs? What can FRB tell us? The DM is a new observational window for cosmology showing similar thing. The lower right panel, this was done by my previous student, Charlie Walker, and you see the lower right panel show that the mean portion of the DM coming from the filaments. And for the lower left plane, he just take one typical line of sight as an example, and he shows the cumulative DM as a function of the distance shown here. And if there's some jump if the line of sight intersect with a halo, but they are rare. The majority of rising up, this cumulative rising up, is due to the intersection of the line of sight with filaments. In this case of 1,000 total DM, the filament contribute up to 80%. But I now want to just push it a little bit further to dissect this contribution. So where are they? So let me just clarify the nomenclature. In cosmology, the IgM is almost identical to the cosmic web, which is describing the structure above 1 megaparsec. Also, there are two other terms, the ICM, the intracluster medium, roughly covering the size of a cluster, and even smaller one would be the CGM, the circumgalactic medium, describing the material surrounding the galaxies. So these two things are really close to each other. It's not well clarified, not well separated. They are related, but not well separated. Okay, so let's see where are these contributions. So this is, again, the current work we are doing. You can see the CGM component describing the material around galaxies is actually higher. Look at this gray line here. It's actually higher than the galaxy itself. And for filaments, which is over here, that is really make a lot of contribution, and is mainly the one dominated IgM components. Okay. And void also have some small contribution, but non-zero. Okay, right. Okay, it's here. Okay, so let me just. Okay. So apart from filament, you can see the gas in the void is non-negligible, although smaller than filament. So now I just want to push it a little bit further. Can we find evidence of the gas in void? And can we find those very weak signals that still contribute to the total DM? Okay, the answer is yes. This is again currently this is from Senyayev-Zodovich effect. The left panel is a result from stacking the EBOS CMAS void catalog on the Planck SM map. And you can see that there's a detection of 3.4 sigma of the gas inside the void. And the right one is what my student is doing, is stacking the void in low Z of the Sloan on the ACT map. He found 5 sigma detection of the gas in the void. So there is clearly a signal in the void, and we should think some interesting estimate, some useful one to pull it out from the FRB. And this is still the ongoing work of myself. All right. So in summary, I find there's no missing baryon. So the additional figure of merit, including the localized FRB to constrain cosmology, may not be significant. It relies on the host galaxy knowledge and assumption of the background IgM. So the true use of FRB is to probe the IgM. So there's no missing baryon in the IgM. It's just a problem of locations. And most of the baryons are in the phase of the warm-hot intergalactic medium with temperature in between 10 to the 5 to 10 to the 7 Kelvin, which are not directly observable with X-ray observations, but with SZ effect and FRBs, and things can be gradually clarified. And we show that a 1,000 local FRB, the diffuse gas fraction can be quite accurately determined, including the redshift evolution. And we use the illustrated TNG simulation to show that the majority of the intergalactic DM come from the filaments, but non-negligible components coming from the cosmic void, which these two are the most difficult ones to find it out. The future study should focus on cross-correlating the 3D information of the loss cell structure and FRBs to disentangle gas in different environments of structures. And we are open for collaboration for source and devise new estimator and such. Thank you very much. Yeah.
So if there's any questions in the room, just come up to the microphone. But there's one or a few online, so I'll start with one from Khee. So the question is, the census table you showed for where the gas is, that's from the lustratus, right? Have you looked at any other simulations?
So currently the one we are working on is from illustratus, yeah.
Have you looked at other simulations?
The other simulation, you mean?
Yeah.
Yeah, we will plan to use the other, like the Cosmo OWHL and such, and Bahamas, yeah. Mm-hmm.
Thanks. Any in-room questions?
Yeah, I have two questions. One, so please don't think I have no soul, but in the plots that you showed where you had the deuterium as a function of the baryon to photon ratio, the bottom plot was lithium and the dip was way off. And I just wonder if you could comment, as a non-cosmologist, I just wonder, isn't that cause for concern? And then another question was, for your 1,000 FRBs where you showed that, what was the redshift range that you assumed for those? Right.
So for the second question, is easier. It's really up to redshift 3, and it's just follow assume the distribution with GRBs. Yeah. For the first question, for the lithium, yes. On the left, you see the measurement. That is, okay, I may just return this. Can I return? No. Oh, you don't show it anymore. Yeah, so this one, basically this is a measurement from measuring the primordial lithium, whereas this curve is the standard Big Bang nuclear synthesis predictions. And the thickness of the curve, you see there's a thickness of the curve indicating the parameter uncertainty. So allowing the parameters to dangle within their 1 sigma, you get a thickness. And what this means is that the measurement is here, whereas the theoretical predictions from the standard Big Bang is the intersection of this curve with the omega baryon A squared measured from Planck, basically this point. So it means that the measurement over here, look at this is a log scale. The measurement is 3 times lower than the theoretical predictions. So that's a missing lithium problem. And it has been a long-standing problem over there. So maybe the issue is that the measurement is a bit underestimated because a lot of lithium are burned out in outer layer of the star and such. So yeah, this is a remaining issue over here. Yeah. But normally in cosmology, we don't take the lithium that serious because there's a lot of subnuclear processes determined, and we take these two more seriously, and deuterium is the most accurate one. Yeah.
Thanks a lot. So kind of a two-part question. The first is, what sort of sigma IgM do you get out of your simulations? And relatedly, is that really just caused by how many filaments you intersect? And how does your sigma IgM compare to other simulations?
Sigma IgM, what do you mean by sigma IgM?
The line of sight variation in DM that you get from your simulations.
Right. So that is mainly the sample variance, that if you have a big volume, So the line of sight measurement, it has certain variance. So if you vary it, then each of line of sight will have certain variance. So sigma IGM would calculate from, you can either calculate from both numerical simulations by calculating the sample variance, or theoretically, you have a power spectrum, and that sigma IGM will be just a Fourier transform of the power spectrum. Yeah.
Okay, thanks.
No problem.
Okay, there's another question on the Slack, but we'll have to move on for time reasons. So if you could answer the questions on Slack, that would be great. And can we thank the speaker again? So now we're going to have a talk by Esan Mouli Ghosh on constraining the value of Hubble's constant using the Redshift-Dispersion Measure distribution of observed FRBs. And this is a remote talk.
Yes, that's correct. Should I go ahead and share my screen?
Yep, please.
Just a moment. Is my slide visible? And
yes, we can see your slides.
Okay, thank you.
Thanks.
Okay, so hello everyone. I am Esan Mouli Ghosh, a third-year undergraduate student from Mohali, India, and I couldn't be here at the IAU in person, so I'll be delivering my talk remotely. Today I'll be talking about constraining the value of Hubble's constant using the Redshift-Dispersion Measure distribution of observed fast radio bursts. The work has primarily been led by my supervisor, Dr. Clancy William James, and Professor Jason X. Prochaska, but it would not have been possible without all of these people named here who are a part of the craft collaboration, and there's many more. So the Hubble tension is a long-standing problem in cosmology, where early and late universe measurements of H0 have a 4 to 6 sigma statistical disagreement. As you can see from the plot on the left here, there is about a 6 kilometer per second per megaparsec of a discrepancy there. And this is where FRBs can come in as independent cosmological probes due to their extragalactic and bright nature. We get 3 types of data from FRBs: the dispersion measure, the signal to noise ratio, and the redshift in some cases if the FRB is localized. So first we model the dispersion measure of FRBs by dividing the contribution into an extragalactic one due to the intergalactic matter, which we term as DM cosmic, and due to the host galaxy. And then we term the contribution due to the Milky Way as DM local. And this includes the Milky Way ISM and the Milky Way halo. So we model DM cosmic as, according to McQuart and Inouye et al., the expected value of DM cosmic goes like this. And once you put in the values for the average electron number density, the density of baryons, and the critical density, you get something like the expected value of DM cosmic varying as omega b H0. Now, in our work, we use an omega b H0 square prior from BBN and Planck CMB since it's determined to about 1% accuracy. And we use all of the cosmological parameters from Planck 2018 cosmology. Now, once you put all of that together, you end up with the expected value of DM cosmic varying inversely as your Hubble's constant. And you can see this from the plot on the right here, where the blue line is the expected value of DM cosmic, or the McQuart relation. And as you increase Hubble's constant, the slope decreases. Now I'll talk about how we model the other contributions to DM. DM host is modeled as a log normal distribution corrected via a 1/1 plus z term. It's parameterized using these 2 parameters, mu host and sigma host. We take the DM Milky Way halo value to be 50 parsecs per centimeters cube according to Prochaska and Zen, and we calculate the contribution due to DM Milky Way ISM by using the NE 2001 electron density model. But other than this, our work also includes other properties of the FRB population, specifically the energetics, which is modeled as a sector function with the parameters Emax and gamma. And the FRB population is modeled to evolve according to the star formation rate raised to the power of n. And the FRB rate itself is modeled as frequency to the power alpha. We also include other observational biases like the FRB width and the beam shape of the telescope and DM sensitivity, but I'll not have time to talk about these in my talk, so I would gladly encourage you to watch Clancy's e-talk Beyond H0, where he goes into detail on all of this. So what does our ZDM space look like? Now here, plotted here is the DM extragalactic on the y-axis and redshift on the x-axis. The color by here shows you the log 10 probability of DM given Z. Now the red dots here are the localized FRBs from the ASCAP survey over 3 different frequencies, and the dotted red lines are the unlocalized FRBs. Now from a first glance, you can see that the PZDM PDF is highly asymmetric with a long tail at large DMEG values. This is due to the nature of cosmic structure, where you can pick up high DMs by intersecting through large-scale structures like galaxy clusters, and also partly due to our adopted log normal distribution of DM hosts. What might be a bit surprising is that at the highest DMEG values, PZDM tends towards a lower redshift for an observed survey. This counterintuitive effect is because you have lower sensitivity to high DM events for a telescope due to DM smearing and other observational biases. Now, plotted here are the 95% contours in the ZDM space. The blue, black, and red lines represent increasing H0. As expected, models with a higher H0 tend towards a higher DM extragalactic. However, they also extend to higher redshifts because increasing H0 with all of the cosmological parameters fixed leads to a smaller universe. Thus, surveys with a given flux sensitivity can observe FRBs to a higher redshift. As expected, this effect is actually partially degenerate with the energetics, specifically the parameter Emax. This is because if you decrease Emax and therefore in general the flux received from FRBs, the same survey will only be able to observe FRBs up to a lower redshift because it's just not bright enough. When you look at the dotted contour line here, you see that the redshift extent has been greatly reduced from the red line here, even though they both have the same value of Hubble's constant, which is 80 kilometers per second per megapascal. And this is because the dotted line is plotted with a log Emax of 41.3. So now we have our model, and all we need is the data. We use 16 localized ASCAP FRBs and 60 unlocalized FRBs from Parkes and ASCAP, and we do a maximum likelihood estimation over a 7-dimensional cube of parameters. Now, these are the bested values and the descriptions of all the parameters that we've used in our work, but what we are interested in is a result on H0, and this is here. We get a value of H0 to be 73 plus 12 minus 8 kilometer per second per megapascal. Now, our value agrees with the value of H0 derived from local universe measurements, but it is also within 1 sigma of early universe DMD measurements. Specifically, 67.4 is pretty much within our 68% confidence interval. So we can't resolve the current discrepancy yet, but there is more to the story. A very important thing to notice here is this dashed gray line, which shows the constraint we would derive if we had held all other parameters constant. Looking at this, you can see the importance of performing a multi-parameter fit and marginalizing over other FRB nuisance parameters. Even in the case that values are well guessed, like in our case where we've used best fitting values, ignoring the confounding effects of uncertainties in these parameters leads to a biased and artificially too precise estimate of H0. Now, another thing you may have noticed is that our constraint on H0 is not symmetric. We derive a relatively sharp lower boundary with looser constraints on larger values of H0. This is the result of what we term as the cliff effect. This occurs because large excess DM above the mean can be induced by intersection with galaxy clusters or because of the long-tailed host galaxy contribution, like you can see here. But even cosmic voids contribute a minimum DM cosmic. So an FRB passing through only voids in the IGM will still have a minimum DMEG. And remember that low values of H0 imply a higher value for this minimum DMEG. So if this minimum is contradicted by even a single measured FRB, those values of H0 can be excluded. So basically what we're saying is if your localized FRB falls anywhere within this area here in the PZDM space, you can exclude that the value of H0 that drags this distribution down, which is a lower value.
You have about 2 minutes left.
Yep, I'm almost done. So In the future, several experiments promise to greatly increase the number of localized FRBs, such as the Kraft coherent upgrade to ASCAP or CRACO. I'll not be speaking about CRACO since it has already been done by Khee in a session before, but we expect an order of 1 FRB per day. And this is really exciting. Now, we have a Monte Carlo realization of 100 CRACO FRBs here, and we compute the posterior probability of H0 and recover the through value consistently. However, what is more exciting is that with 100 localized FRBs, we have now reduced our statistical uncertainty to plus minus 2.45 kilometer per second per megaparsec. And this will provide us with 2.5 sigma evidence to discriminate between that 6 kilometer per second per megaparsec difference in early and late universe estimates of H0. So just to conclude, I would like to say that we obtain a best fit H0 of 73 plus 12 minus 8 kilometer per second per megaparsec from 16 localized and 60 unlocalized ASCAP and PARCS FRBs. Even though our current constraint on H0 doesn't provide us with the statistical power needed to discern between late and early universe measurements of H0, there is great hope for the future. Just a year's worth of 100 CRACO FRB observations will provide us with a statistical uncertainty of about 2.45 kilometers per second per megaparsec. Within the next few years of CRACO, with sufficient follow-up time for localization, we expect 400 FRBs to give us a statistical uncertainty of about 1.2 kilometers per second per megaparsec. And keep in mind, this includes the increased variance when fitting for other parameters of the FRB population. So, and when you look at this plus minus 1.2 kilometer per second per megaparsec is actually comparable to uncertainties right now when measuring H0 using supernova and C-feed distance ladders. So we need to focus on systematics, which would otherwise limit this. And I would just like to say that a sophisticated study of FRB distribution in ZDM space is required, which includes observational biases and also includes correlated parameters like the energetics and the DM host. I'll mention some of the systematics which might play a role in our model, which is basically the fraction of the galactic feedback, the function and the value of DM host that you take, and also the DM Milky Way halo, which is not very well constrained. But all of that is said in detail in Clancy's talk. So please, I would urge you to look at that whenever you get time. So I'm done. Thank you.
Thanks very much. Are there any questions in the room? If so, can you come up to the microphone? I'll start with one online. So this is from Khee. You might have said it and I missed it, but what are you using for FIGM uncertainty?
Right. So we actually have not included that in our model yet, and that is one of the systematics that we'll be looking at in the future. So it's very important to look at the uncertainty due to FIGM, and there's a plot in the paper that I've not put in the presentation, and I could send you the link and you could look at that. But as of now, we believe that this uncertainty can be taken into the values for sigma and mu host that we derive. FeatureWorks will definitely require to use that as a free parameter.
Thanks. Okay.
So basically, you fix your value of omega baron from the CMB results, right? So, but for the limited number of sideline, like the 16 localized, then there is some variance in between, which is degenerated with the F sub D. So omega baron is actually degenerate with F sub D in the measurement of DM. So I think you probably need to take into account that variance, which will amplify your error bar. Yeah, I think that's a common question. Yeah. Mm-hmm.
Yeah. I think I agree with you, and that is why it's very important to look at the systematics. And FD Z is taken from McQuarrie et al. And taken according to Prochaska. I forget the date of the paper. So in future models, we'll definitely keep that as a free parameter and also fit over that. And yeah, it'll definitely probably increase the error margin by a little.
Thank you. Okay, let's thank the speaker again.
Thank you so much.
Okay, so next we have Khee Lee, who's going to talk about the FLIMFLAM survey for FRB foreground mapping, and this is also a remote talk.
Shall I share screen?
Hi.
Can you hear me?
Yes.
Shall I share screen?
Yes, please.
Hi, okay, can you see my slides?
Yep, looks good.
Okay, all right, thanks, Kenji.
Thanks.
So today, thanks a lot for the organizers for giving me the opportunity to do this talk. Unfortunately, I was not able to make the trip in the last minute, so I'm giving the talk remotely. So today I'm going to tell you about a project that we've been doing over the past year and a half or so to basically study the cosmic baryons using fast radio burst and galaxy surveys. So just to start with credits, there's several postdocs at IPMU and students as well who have been working on this project, as well as collaborators, including Xavier Prochaska and Sunil Simha at UCSC, Nicolas Tejos at Católica Valparaiso, and Jeff Cook at Swinburne. And also to give a very big credit to the craft and F4 teams, because we are basically a downstream analysis from their efforts. So a lot of the stuff I'm going to be talking about is going to be based on this paper that we published earlier this year in FJ. And there's also a talk by Ilya Krikin that's one of the e-talks that goes into a little bit more detail into what I'm going to talk about. So we've seen already that the dispersion measure of the FRB is the integral of the free electrons along line of sight. And given that vast majority of baryons in the universe are ionized, it's a powerful probe of cosmic baryons. And we've already seen this McCord relation, the beautiful result that the DM, the extragalactic DM contribution as a function of redshift from FRBs is consistent with the omega baryon that we expect from lambda CDM cosmology. So this beautiful result showed that there's no longer a missing baryon problem, but as we heard from Yin-Zhe earlier, there's still major questions of where the relative locations of where these baryons reside. So I'm not gonna go into this slide, go into detail here. We've already heard that various efforts using quasar sightlines or even X-ray measurements have tried to put a dent on this problem, but still a large fraction of the missing baryons it's unclear where they are until the FRB McCord result came out. So I want to make a quick layout the picture of the picture that I'm going to be working with, which is that the DM of the FRB can be decomposed into the Milky Way component, the host, which is from the FRB host galaxy, and then I'm going to make the distinction of so-called DM IGM and DM halos. So in the literature, usually we hear that the extragalactic component might be called DM cosmic or DM IGM, but here we're going to explicitly split it up into these components, of which one comes from the cosmic web large-scale structure, another comes from intervening galaxies that are intersecting the line of sight of the FRB. So the premise of my talk is that if you know if you have spectroscopic data of both galaxies in the foreground as well as tracing the cosmic web in the foreground of the FRB, you have vastly more information on the cosmic baryon distribution. So the basic idea has already been applied by Sunil Simha in a paper studying this FRB 1906-08, where they grabbed spectroscopic data from the Sloan Digital Sky Survey and analyze the DM contributions from the IGM as well as individual galaxies that lie close to the sightline. So in this analysis, they studied the contributions assuming a given model of the CGM and a given fraction of IGM in the universe. But the next step that we would like to do is to obtain a large sample of foreground data such that we can set the models of the IGM and CGM as free models and constrain them using the data. In our paper earlier this year, we looked at the relative contribution of the variance in the dispersion measure. So at fixed redshift, the cosmic dispersion of the cosmic dispersion measure shows a variance around the mean that is quite sizable. And in the paper, we looked at the simulation and found that at, say, redshift 0.3, there's roughly an equipartition of variance between the large-scale IGM as well as individual halos. So, roughly half of the variance here comes from the large-scale voids and filaments, and roughly half comes from individual intervening galaxies along the sightline. And also we found that, and then we asked a more direct observational question: how deep do you need in your observations to study them? We found that if you're looking at contributions from within 1 arc minute, of which they contribute in total about 30% of the total DM, the FRBs will the galaxies tend to go as faint as 24th Mach, but if you go beyond an arc minute, the galaxies are going to be a bit brighter, about 22nd Mach. So this motivates a multi-tiered strategy to observe the intervening galaxies. So for the cosmic web, there have been surveys like Sloan and Gamma that have targeted the cosmic web, and this requires a different type of telescopes, smaller but wide field multi-object spectrographs. And so the next step was motivated by this kind of survey. The problem is that most of these surveys do not cover the fields where FRBs have been discovered in the past year. So we've been motivated to design specific observations to target FRB fields with multiple facilities ranging from IFU observations on 8 to 10 meter class telescopes to target the faintest sources closest to the sightline, a bit further out for a larger more massive galaxies in a few arc minutes, and then wide field spectroscopy with 4 meter class telescopes. So the main component of this is the FLIMFLAM survey, the FRB line of sight ionization measurement from light cone AO omega mapping survey. And that is conducted on the 4 meter Anglo-Australian telescope, which is in Australia. And it has it's a spectrograph that has observed 350 galaxies at once over 3 square degrees. And our overall goal is to target around 20 FRB fields. So the basic strategy is to target a single pointing of 3 square degrees in front of each FRB. And then we will use a simple magnitude limited selection to target FRB. So here we show preliminary data in front of FRB 180924. And then, so basically there are typically around 2,000 to 3,000 galaxies per field, which requires about 1 full night of observations to target. And then subsequently, we will use density reconstruction techniques to directly identify the filaments and voids in the foreground of the galaxy. So we've done some forecasts for how this information can help us constrain the missing baryon problem. So the initial science goal is kind of using the most simple possible model, which is simply splitting the cosmic baryons into CGM and IGM component. So we forecast that with around 30 FRBs, we would get a sub 10% precision on FIGM and FCGM to within 1 or 2%.
You have
so
about
in this,
1 minute left.
Okay, so in this analysis, we model DM host. We do address the fact that DM host is an unknown parameter, and we model it as a Gaussian distribution with unknown mean. Please, I'm not giving any details here, but please see Ilya Krikin's e-talk for more details. And in future analysis with more detail, we hope to be able to study the characteristic scale of the CGM as well. Just to give a sense for what we might try to constrain. I'm working with Daniel Sorini at Edinburgh, who has run SIMBA hydrodynamical simulations that have different feedback models. And the basic quantity that we do see is that the fraction of the CGM relative to the IGM changes depending on feedback. So this is going to be one of the basic parameters that we are going to observe. So I will start to, I'm running out of time, but the bottom line is we now have over 20,000 new galaxy redshifts in front of this 10 or 12 FRBs, and then an analysis is currently ongoing. So I think I will just stop here and take questions.
Thank you. Are there questions in the room? Could you introduce yourself and then ask your question?
Sure. My name's Liam Connor. Thanks for the talk. And I really liked your paper as well. My question was about your simulation. Why did you choose to use Millennium rather than illustrious TNG, for example, where you don't have to choose a baryon prescription?
So I think the basic reason was that we wanted to be able to define to be able to define a parametric model that we might be able to apply on real data. So if we picked TNG, for example, it's kind of a fixed hydrodynamical model where it might be unclear how you would, try to model the halo CGM in a mock observation. So I think the bottom line is that we wanted the freedom to be able to set our own model. So we did check, we did do some consistency check to verify that our statistics of the DM IGM, DM halos was roughly consistent with illustrious. And I think subsequent studies, I believe that the study that Yin-Zhe showed at the end, I believe they are roughly consistent with what we had as well.
Thanks.
Okay, we're running out of time, so thank the speaker again, please. And the next speaker is Sunil Simha, who I think is here. Yep. And he'll talk about searching for the source of excess extragalactic DM of FRBs.
Okay, hello everyone. My name is Sunil. I am a graduate student at the University of California, Santa Cruz. And today I'll be talking about some of the fields that we have been analyzing as part of the FLIMFLAM survey, the fields that have a large excess of extragalactic DM. So without further ado, let's get started. So this plot has been probably shown every single talk today, but it is important for us to remember what the McCart relation is. It's basically the fact that the DM cosmic, or the cosmological DM between us and the FRB is a function of redshift, and it follows known, it follows basically from the lambda CDM cosmology that we have pretty good awareness of. Over this, of course, we can plot what is the PDF of the expected DM versus redshift. So for each redshift, we could expect a certain distribution for the DM. Based on cosmological variance, there could be a lot of halos, filamentary structure. Basically, there is a PDF that shows up. Here you can see that I've plotted the median and the mean value. The mean, of course, is the McCart relation, but you notice that the median is below the mean. It's because the large DM tail is primarily because of multiple halos in the sightline, and that is a rare phenomenon. So it is more likely that there are fewer halos in the sightline, and therefore the median is lower. Now, on top of this, we could plot the localized FRBs. So what I've done over here is subtracted the Milky Way and host contributions. So of course, assumed these values. So, well, the Milky Way ISM can be modeled with NE 2001. I've assumed a value of 50 parsecs per centimeter cube for the Milky Way halo, and roughly 80 parsecs per centimeter cube for the host and its halo. So if I do that and I plot all the localized FRBs, this is what it looks like. And you might notice that there's a significant number of them at all of these large values, XSDM. So it is interesting to understand what is causing this sort of excess. So there could be multiple reasons. One of them, of course, is that there are a large number of foreground galaxies or foreground galaxy halos in the sightline. The other reason is that there's a huge contribution coming from the host or the progenitor environment itself. Maybe there's excessive cosmic web contribution. Probably not, at least according to some simulations done by Ilya. It is unlikely that both the the halo contribution is small and the IGM contribution is large. So it's mostly just the first two reasons that drives this, can drive this XSDM. So, of course, KG gave a very nice talk about the FLIMFLAM survey, but in case someone missed it, here is a very brief description of what it is. Basically, get spectroscopic observations of an FRB field, trying to understand what the matter distribution of galaxies are like, so that we can reconstruct it and get the DM independently from the radio measurements. So of the 4 fields that we have targeted, 4 of these have excess extragalactic DM, which are listed over here. One of them is, of course, very interesting, the 210117 FRB. That's very large. So I'll be talking about what might be the reason for that. So for our data, we have AA omega observations of galaxies brighter than 20th magnitude in R, Deimos and Elbrus observations of galaxies which are fainter than 22.5. And for 190714, we have Muse data cube as well. So we've got really deep data in the nearby vicinity of the sightline. So basically what I'm doing is getting where the location of a foreground galaxy with respect to the FRB sightline. I estimate the mass using SED fitting from a software called Segal. And using the mass and the stellar to halo mass ratio from Moster et al. 2013, I can then get a halo mass. And assuming a halo model for baryons, in this case, Francesca and Zhang 2019, the modified NFW profile, I can get a DM contribution once I input the redshift and the impact parameter. So you just repeat this for all the foreground galaxies near the sightline, and this is what it looks like. So this is 190714. So basically, we start by taking out all the stars. We just ignore them. Then we identify the background galaxies. These will, of course, not contribute dispersion measure. And then we get the foreground galaxies. So in this case, for 190714, you can see that there are quite a few foreground galaxies that contribute quite significantly to the dispersion measure. So much so that if we were to look at the dispersion measure contribution from the halos, which is shown here on the plot on the left, and compare it with an average sightline, which is the dotted line, you see that there is quite a bit of excess. So there are a lot of halos in the foreground of this FRB. I can then take another step and add an average IgM contribution. As Khee mentioned, this is from the filamentary gas. So if I just add that, and then I compare it to the value that I had in the McCart plot earlier, so that's the red point, you see that it is more or less able to explain all the where that excess is coming from. In this case, it is mostly from the foreground objects in the sightline. So this implies that my guess for the host galaxy's contribution, which is 80 parsecs per centimeter cube at the host redshift, is not too bad at all. So it is very unlikely. It's unlikely that the host contribution is a lot more than this is. So for this sightline, it was mostly the foreground objects contributing to the excess DM. Now, if you go to 210117, which is the other interesting sightline, we see that there are barely any foreground galaxies out there, and they contribute very little to the FRB dispersion measure.
You have about 2 minutes left.
Okay, thank you. So I can play this game and say, okay, well, what is the maximum amount I can get from this model? So I increase the radial extent of the halo gas in my model. So usually I take the halo gas extents up to 1 virial radius. In this case, I extended it up to 2. So there's more matter to intervene. And I also added so I added 30% more IgM contribution than what usually is. And it still falls very much short, as you can see quite dramatically here in this plot. So most of the excess DM must be coming from the host in this case. So with this, I won't be going too deep into the other two sightlines. They show pretty much the same results as 210117. So 3 out of the 4 sightlines that I have analyzed show a large excess extragalactic DM coming from the host galaxy. So it begs the question, do most high excess DM FRBs have a large DM host? From what limited sample I've analyzed so far, it appears to be the case. Of course, more work needs to be done. It's just 4 FRBs that we have worked on so far. There are caveats, of course. We have yet to include DM halo from galactic groups. So this is gas and halos that are not really part of the CGM of galaxies, but more like group matter. So this is a work in progress. So far, we don't have very strong indication of large nearby groups in any of these sightlines, but that needs to be carefully inspected. Yeah, so of course, there's I forgot to add this point here, but there's always the caveat that the Milky Way halo itself is somewhat less constrained in terms of what its contribution could be. So, well, maybe once we have a full analysis from the FLIMFLAM survey, we hope to be able to start answering some of these questions. So with that, I end my talk, and happy to take any further questions. Thank you.
Okay. Yeah, go for it.
Okay, great talk. 2 questions. One, the dashed line that you were showing for DM cosmic, that's just a mean value?
That is the mean
for the
value.
IgM? Okay.
Yes.
And then second question, where does this value of 80 parsecs per cubic centimeter for the host DM, like where does that assumed value come from, and why bother subtracting it? Couldn't you just essentially do the analysis you were doing without subtracting that value and then just turn that into a constraint on DM host?
Well, yeah, that's a good question. So the 80 mostly comes from like some of my previous work on 190608. That was one of the typical values of, or well, if you look at the host contributions of FRBs, 80 is somewhat on the higher end of things. So that's what I thought, well, maybe it would be a good idea to see how far I can get away with, and like how much excess would still exist if I subtract this contribution. Of course, I could do this analysis without, and I don't think the results would change all that much. So, thank you.
Hi, thank you so much for the talk. So I wanted to understand how you decide that something is, probably a contaminating foreground. So I see the position, like they kind of overlap. So is that what you use, or do you consider the redshifts as well?
Sorry, could you repeat that? So are you asking?
Yeah, so for the foreground that you pointed out, are you considering them also based on their redshifts, or is the position okay?
Sorry. Yeah, I should have made that clear. But yes, redshift is a very important input. So basically, we know how where the foreground galaxies are irradially, and also how far away they are from the sightline. Because we know them, we know the radial distance. Okay, so is there like a threshold that you expect, like a redshift threshold that for what you think should be contributing definitely to? Right. Yes. So we get redshifts from the spectroscopic surveys that we did, and therefore we know. Well, if we assume that model of the baryonic matter that I told you earlier, so if we assume that, then we would expect this amount, a certain amount of dispersion measure from that particular halo sightline. Okay, thank you. I'm also wondering, like the H2 regions and the star-forming region, did you like? Oh, we're talking exclusively about galactic halos, so this is not taking into account galaxy IGM, ISM at all. Oh, thank you.
Okay, so there's one more question. If it's quick, then you're good. No?
Hi, thanks for the very clear talk. So I guess that the future of cosmological use of FRBs would be to do the two-point correlation function, right? So if the excess dispersion measure is indeed mostly due to the host, do you expect this to be a problem for this type of cosmological use? And if is there a way to mitigate this if it's the case?
Yeah, so yeah, the host contribution is going to be, well, if it is the likely cause of this, then yeah, I can see that being a problem. And I guess so far, I'm not entirely sure how to mitigate this. I have not really thought about it deeply, but it's a very interesting question, and so thanks for asking me about it.
Yeah, thanks.
Okay, thank you. So next we have Liam Connor, who's going to speak about what can we expect from FRB gravitational lensing.
Okay, so I want to try to cautiously forecast what we might expect from the next few years to a decade of FRB gravitational lensing. And I'm going to try to use my 13 minutes to step through more than 15 orders of magnitude of lens mass. So when we think of strong lensing, we usually think of these striking images where you either see an Einstein cross from a quasar being lensed by a massive galaxy, or a Einstein ring. More recently, of course, this very striking image of strong lensing around a galaxy cluster. Now, if the objects being lensed were transients rather than high redshift galaxies, then each of them would have its own time delay, right? And they would arrive at different times. And the amount of time delay would correspond to the geometry of the system and the mass of the lens. And this is the idea with FRB gravitational lensing. You'll make a detection of one copy of the burst, and then one or more copies will come afterwards, and that delta t, the time delay, will give you information about the geometry of the system, and again, the mass of the lens. Now, the thing that's special about fast radio bursts is not just that they're narrow and so we can get lensing time delays down to a millisecond. You can actually do better than that. And this is a GIF created by McGill graduate student Sreef Khader, which I think explains this point. Because we in the radio preserve voltage data, we have phase information, we actually have the electric field waveform itself, we can, in principle, go down to time delays that are roughly 1 over the bandwidth of the instrument, so nanoseconds at a gigahertz. So outside of the radio, I think this takes people a while to grasp, which is why this GIF is handy. The idea is you would take a voltage time stream, and you would either cross-correlate that burst with another potential burst, or autocorrelate the burst with itself to look for time lags at non-zero lags to look for evidence of a repeat copy of the burst. And by the way, if you want to go into the nitty-gritty of this technique, I strongly recommend these 2 papers put out by the Chime FRB collaboration, one led by Zarif, the other by Calvin Lung. They really commence the field of what they call gravitational lens interferometry. But the purpose of my talk is to forecast what we might expect from future surveys. So what I'm showing here are the enormous range of lens masses and time delays that you can access with FRB gravitational lensing. So on the top panel, you see delta t. So this is the time delay between 2 typical bursts as a function of lens mass. And the bottom panel is the angular separation from lensing. So you can see you can go all the way down from sub-microsecond duration, so machos, primordial black holes, stars, free-floating planets, up to what you might call milli-lensing, so IMBHs, dark matter substructure, up to where you can do the cosmology, so time delay cosmography, going after H0, things like this, with galaxy scale lenses. So you can go down from, again, in principle, 1 over b, all the way up to the duration of the survey, more than 15 or 16 orders of magnitude in time delay and therefore lens mass. Okay, so if we're going to consider future surveys, things like DSA 2000 and CHORD, where we're going to be more sensitive, we first need to forecast how many FRBs they'll actually find. And so we have to make assumptions about source counts, the brightness distribution of FRBs. And the good news is there's a lot going on in the millijansky millisecond radio sky. We don't run out of FRBs when we go down to 10 Jansky milliseconds. From fast blind detections, we find that there's of order 100,000 events across the sky each day at about 10 or 20 millijansky milliseconds. So this is good news for CHORD and DSA 2000 and SKA. Okay, so DSA 2000, if you haven't heard of it, it's a proposed telescope that will go in a valley in Nevada. It's 2,005-meter dishes, observing between 0.7 and 2 gigahertz. It's got an SEFD of 2.5 Jansky, so it's roughly the sensitivity of Arecibo, but with 500 times the field of view. Okay, so for FRB detection purposes, it's like pointing 500 Arecibos at different locations of the sky. CHORD is another ultra-wideband, wide-field survey. The SEFD will be more than 5 or 6 times better than CHIMES. Okay, so it'll find a lot of FRBs as well. And then I'm going to forecast for something that I call a coherent all-sky monitor, or a CHASM. So the idea here is to do away with dishes altogether. You have a dense aperture array, so you pack a bunch of antennas, you point them at the sky. Because they're evenly spaced and potentially on a grid, you can FFT beamform and search the whole field of view. And in this case, you get access to 5 to 10,000 square degrees. Okay? So a good example of this is the recently proposed BURST telescope, led by Wei Li Pen and a group in Taiwan. But for the purpose of these forecasts, I'm going to assume that this CHASM, as I'm calling it, has the sensitivity of CHIME, okay, but with 25 times the field of view. So BURST 2048 is, I think, an SEFD of 600 Jansky, so it's not quite at this level, but I'm envisaging something in the future. Okay, so CHORD DSA 2000 should find and localize several thousand FRBs per year, and this CHASM might find 10 or 25,000 FRBs per year. Okay, so one thing that I think has been neglected when people talk about FRB gravitational lensing is the importance of the redshift distribution of the sources that you're studying. Okay, the optical depth of lensing is a strong function of redshift, and it goes like z cubed for lowish redshifts in the case of strong galaxy lensing, and it goes like z squared for point masses. And so if you're only probing the nearby universe, you really don't give yourself a lot of optical depth. The probability of seeing a source lens is very low. And you can see that here in this figure. If you just look at the CHIME FRB redshift distribution modeled from their DMs, for the median redshift, say 0.3 or 0.4 or so, the probability that a sightline is lensed by a massive galaxy is going to be less than 10 to the minus 4. So there really is an advantage to more sensitive surveys and deeper redshift distributions. And so you get this trade-off between field of view and sensitivity if we compare the chasm I mentioned before with a 50 Jansky SEFD, but 5,000 square degrees or so, with DSA 2000, you get a lot more optical depth by going to higher redshifts, but you give yourself more sources by having this enormous field of view. So one of the first things people hope to do with FRB gravitational lensing is to go after compact sources of dark matter. So machos or primordial black holes. So PBHs are proposed to have come into existence in the early universe. There's various mechanisms for how they formed. But microlensing by FRBs is a good way to go after them. If you run a 5-year survey and you see no evidence of lensing on timescales of, say, a microsecond to a millisecond, you can rule out the fraction of dark matter that's in PBHs. Okay? So we find that with CHORD or DSA 2000, after a few years of observing and not seeing anything, you can rule out the fraction of dark matter in PBHs at the sort of 10 to the minus 3 level, which is a useful region of parameter space. It complements some of the other probes.
You have about 2 minutes left.
Okay. Okay, for the other results, it's not usually a good idea to just plop a results table in a paper, but let's step through these one by one. So I think the most surprising thing that we found when writing this paper is that the sources that are going to dominate gravitational lensing are stars at cosmological distances. So the optical depth due to stars in distant galaxies is quite large. And the basic argument is this: if you imagine an elliptical galaxy, massive elliptical galaxies tend to dominate gravitational lensing optical depths. Within the inner 6 or so kiloparsecs, the optical depth due to lensing by a star is of order 1. And the aerial coverage, the amount of sky that's covered by the inner 6 most kiloparsecs of elliptical galaxies is something like 10 to the minus 3 at a gigaparsec. And so we come to the surprising conclusion that CHIME, if it had of order 1,000 or 2,000 voltage jumps for FRBs, should expect to have a strongly lensed FRB from a star. Another thing you can do with this is if you discover that an FRB is microlensed at sort of the 20 microsecond level, like with DSA 2000, it's also probably strongly lensed by the galaxy itself, and so you should follow it up in the optical and see if the host galaxy is smeared out or if there's evidence of lensing. And then you can maybe put a different telescope on it and wait for that burst to show up a week or two later. Okay, we already did primordial black holes. And the sort of millilensing phenomenon, we can go after intermediate mass black holes. Here you would expect lensing delays of about 100 microseconds to 100 milliseconds. And again, if you don't see anything, you can constrain the volumetric number density of IMBHs, and this is useful for formation channels and LIGO and things like this. If you take seriously, on the other hand, that millilensing has already been detected by a GRB, a BATSI GRB, which was claimed in a paper this year, then CHORD and CHASM and DSA 2000 should expect to see millilensing events of FRBs by intermediate mass black holes. Okay, and finally, for the sort of classic cosmology with lensing, time delay cosmography and the Hubble constant, things like this, you really do want a galaxy scale lens. The problem is if you have a transit instrument and you're not always pointing at the same direction in the sky, it's very, very unlikely that when that second burst shows up, you'll actually be pointed at the same patch of sky, right? And so you either always want to be searching the north or south celestial pole, or you want to have an enormous field of view like the chasm that I described before. So a CHIME-like survey that had maybe 5,000 square degrees and which was always looking at the NCP could find 5 to 40 of these galaxy-scale FRB lensing events in a few years on sky. I might just race through this. I've talked about this before in other contexts, but if you do have one of these galaxy-scale systems, you get a really clean probe of the CGM of that lensing galaxy. So the only difference in DM and RM between the lens copies is going to be from the halo itself. So this is a very clean measure. Okay, so to wrap up, FRB lensing offers some really unique cosmological applications, all the way down from sub-microsecond time delays up to potentially years of time delay, galaxy groups and small clusters. And this corresponds to more than 15 orders of magnitude in mass. The problem is it's a really rare phenomenon, very difficult to detect, and it's highly dependent on redshift. So you really do want to have a lot of sensitivity and probe FRBs beyond redshift 0.5. Somewhat surprisingly strong lensing by stars, we think, will dominate at short lags, and my bet would be that the first time we detect FRB gravitational lensing, it will be due to a star at a cosmological distance. And finally, coherent all-sky monitors, for example, BURST, or targeted pointing observations, like with DSA 2000, could find galaxy-scale lensing events with which we could do time delay cosmography and go after H0. And I'll end there. Thanks very much.
Okay, I don't think we have any time for questions, but there are, I see a few people in the room that want to ask questions and also a few online, but there's a coffee break after this, so maybe bombard Liam with your questions then. Okay. Sorry. Okay, so the last talk this session is Mawson Sammons, who will talk about the effect of gravitational lensing on fast transient event rates.
Hiya, can you see my slides?
I can, yes.
Awesome, thanks. So yeah, I'm Mawson Sammons. I'm a PhD student with the International Center for Radio Astronomy Research, and I've been working with Kath Trott, Clancy James, Mark Walker, and the late J.P. McCart as part of the CRAFT team to understand the effect of gravitational lensing on fast transient event rates. And before I get kicked off, I'd just like to acknowledge the traditional custodians of the land that I'm giving this presentation from, the Whadjuk people of the Noongar Nation, and I'd like to pay my respects to their elders past, present, and emerging. So why fast transients? Well, fast transients are oftentimes emitted from a compact region at extragalactic distances, which gives them some of the most angularly narrow objects that we can observe. This makes them sensitive to gravitational lensing from extremely fine scale mass structures and some of the lowest mass lenses that we can access that might have been smoothed over by sources of a greater extent. Now, from extremely low mass lenses, it's going to be quite difficult to discern the presence of lensing in an individual burst, and so we're much better served by treating the whole population. To do so, we're going to be using a differential event rate kind of model. So the good news is that it's contained in this equation on the screen. The bad news is that that equation is still relatively complicated, so I'll lead us through it. So as I said, this is an equation for the differential observed event rate with observed fluence. And that tells us effectively how much our observed rate in bursts changes per a change in our sensitivity. It's got some fairly familiar parts to it. So this is the volumetric fluence integration element. It effectively describes how, as we increase the distance that we're observing to, we include a greater number of sources within what we can see, but the fluence that we observe from those sources is going to be greatly reduced. We also have a 1 on 1 plus z cubed cosmological expansion factor to account for bandwidth compression, time dilation, and rate dilation. Then within our integration over magnification, we have the event rate energy function, which is a product of 3 independent functions, namely the redshift evolution, luminosity function, and spectrum of our source population. Then finally, we get to the meat of this equation, which is the probability of source magnification and its gradient mapping factor. Now, for the model that I employed, we used a probability distribution from Rauch, and then a fair amount of more technical details of lensing goes on into fitting this. I won't go into those details here, but feel free to ask me about it later, or keep an eye peeled for the paper that we've submitted on this subject. So now that our model is complete, we can use it to calculate our results, which for our case is the relative effect of lensing on the differential event rate, or DRDF for lensed universe normalized by its unlensed equivalent. We calculate this for a range of fluences relative to a maximum energy burst at a redshift of 1. And because we're plotting a relative quantity, below 1 means a slower change in rate due to lensing, and above 1 means a faster change in our rate due to lensing. We've calculated this quantity for a range of gamma values, where gamma is the power law index of our luminosity function. And for each case, we can see this characteristic dip and then peak structure. Not only does this dip and peak structure persist through changing gamma values, but we can change our intrinsic spectral index of our population, which is how our population responds to changes in emission frequency. And we see that it persists through that. And as well as if we change our redshift distribution of our source population from, say, uniform to with the cosmic star formation rate or its integral. Now, there are a couple of key conclusions to take away from this slide. The first being that the effect of lensing on the differential event rate is capped at about 10%. So that makes it a second order effect in the context of FRB and GRB modeling, where uncertainties in other population parameters tend to dominate. The other thing that we can take away is that in the low fluence regime, the effect of lensing is effectively negligible. In the same way that we can use a local environment sample to model a population without redshift evolution, we can use a low fluence sample of FRBs or GRBs to model our population without the effect of lensing. If we were to do so and use DRDF for a low fluence sample to constrain our population, then extrapolate out to a high fluence regime, we could compare with observables to make this fluctuation something we can actually measure, and then use the observed fluctuation to constrain how the presence of extremely low mass objects. So what mass ranges am I kind of talking about? In order to take that into account, we have to model the wave optics magnification. So we do that here as a function of source position for a range of W values, where W is proportional to frequency. For extremely high frequency cases, such as the light blue, we expect the interference fringes to oscillate quite rapidly, and then a finite sized source, such as a GRB, would average over these oscillations to give us the geometric black line here, and as such, geometric optics is a good approximation for modeling lensing in GRBs. If, however, we had a low frequency case, such as an FRB, we'd expect that for sparsely packed interference fringes, that even a finite sized source will oscillate in magnification as a function of position. This is going to change the cross-section to a certain magnification and ultimately our probability of that magnification. And it's also going to restrict our maximum magnification to some diffractive limit. We've plotted that on the bottom here. If we take this and then some knowledge of how many lenses we expect along a given line of sight, we can actually calculate the minimum probed lens mass for any given transient. So we've plotted that here for a couple of different models as a function of source redshift for a handful of different transients. And these are the geometric optics results. So in the geometric case, we can see that FRBs probe down to the lowest mass scale, followed by GRBs and then supernova. And what we've plotted is in shaded gray, is the currently unconstrained region of primordial black hole parameter space. So theoretically, 100% of dark matter could be comprised of objects kind of in this regime, and we wouldn't have a lot to argue against it. Now, as we can see, FRBs and GRBs are perhaps sensitive to that, but if we incorporate our wave optics calculations, we can see that FRBs are actually restricted to a much higher mass limit that prevents them from kind of doing that. But as you might expect, our GRB case is rather unaffected by the wave optics results, where these kind of wavelengths here are color-coded for transients. And so GRBs may potentially give us a way to probe a currently unconstrained region of dark matter parameter space, which is potentially quite exciting. For FRBs, what we can say is that it's unlikely that we're observing them because they're highly magnified. So this was something that was talked about in the community a little bit. The idea that potentially FRBs could be intrinsically low energy phenomena that are being gravitationally lensed to make them appear high energy. The relevant kind of parameter space here is our lens mass, and then the factor of apparent energy divided by maximum intrinsic energy, which is effectively our maximum magnification. So the shaded areas here are excluded regions of the parameter space. So in the top left, we have these are energetically low energetic phenomenon that are being intensely magnified, and basically wave optics rules these scenarios out because there's simply insufficient magnification to get there. Whereas in the bottom quadrant, we can see that these are intermediate energy phenomenon that are being magnified somewhat. So this is allowed under a wave optics treatment, but if this were the case and all the FRBs where we observed were highly magnified, we would expect to observe a gamma value of -3 because of the shape of our magnification probability distribution.
You have about 2 minutes left.
Thank you very much. So we don't observe our FRB distribution to have something consistent with a gamma -3 value, so we can rule these scenarios out as well, leaving a narrow margin of parameter space where this scenario is still technically allowed, but given the relative areas, it's probably unlikely that that's the case. So with that, I'll hand off to a summary slide, and I'll use a couple of seconds to note that I'm reaching the end of my PhD, so I'll be looking for a job soon. If anybody has any opportunities they think I might be interested in, feel free to contact me by email or on Slack. And with that, I'll pass back to the chair. Thank you very much.
Thank you. Are there any questions before we end this session? Okay, then I guess because we're running a little bit late, then we'll wrap the session up here and continue the discussion on Slack. So can all the speakers make sure you sign on to Slack to answer any questions that are directed to you. And let's thank all the speakers of this session again one last time.